Welcome back. Today we will start with the week 3 of the course of this advanced manufacturing and process modeling. Although some part of week 3, that is the basics of solidification micro mechanism, that we have already covered in the casting section. But we will continue with the die filling analysis, and we will discuss, like I told you in the last class, that although there are analytical techniques, but for complicated geometries, when we are going to develop by casting route, we need to take the help of numerical methods, so that we can simulate the filling and solidification, and thereby we can optimize the process conditions and also the component design attributes. So that we will be discussing in this section of the course. So this is, as I told you, this is the die filling analysis section of the course. So so die casting is a high pressure metal casting process. We have discussed in detail in the casting solidification section of the course. So there you are already aware about the high pressure die casting process, and also you are aware about the gravity die casting process. So where nature of the molten metal flow plays a pivotal role in determining the quality of the final product. So smooth and uniform flow is essential to avoid defects and also such as air entrapment, shrinkage, porosity, blowhole, and also surface defects, imperfections. And also if there is too much turbulence during melt flow, especially in case of light metals, it can cause air entrapment, which can lead to porosity, and also that can significantly damage the structural integrity of the resulting cast part. Whereas shrinkage porosity occurs due to improper feeding of the solidification shrinkage, and because of lack of proper getting design, proper risering design, so that the melt needed to compensate for the density change, which is higher density of the solid compared to the liquid state, which is the primary reason for the shrinkage that takes place. So improper feeding of the melt, improper feeding of the solidification shrinkage causes the defects in the cast part and weaken its structural integrity in a big way. Additionally, disturbances in the flow can also cause visible surface defects. Analyzing and optimizing flow behaviors using tools like computational fluid dynamics helps in a big way to minimize these defects and to optimize the design of the process and the product, and also it enhances the overall casting quality and the casting yield simultaneously. So the factors which affects mold flow, primarily its viscosity, which directly affects the velocity and the flow nature of the melt in the cavity. So like if the viscosity of the melt is higher, like we have discussed in case earlier in case of semi solid die casting. So even at a higher velocity, or even with the pressurized getting system where there is a back pressure involved, we can achieve laminar flow because because of the higher viscosity of the melt, and also other properties such as density and thermal conductivity of the melt plays a vital role in deciding the melt flow, in the nature of the melt flow. And the inertia and the viscous force directly affects the Reynolds number. So as we all know, what is a Reynolds number? So Reynolds number basically can be expressed as rho v d by mu in case of a pipe flow, such as the case which is shown over here, where rho is the density, v is the velocity of the fluid, d is the characteristic dimension, or in this case diameter of the pipe, flow diameter, and then viscosity, that is the dynamic viscosity of the fluid, in this case liquid melt of course, or the solidifying melt, whatever may be the case. So the inertia and viscous force directly affects the Reynolds number, which decides whether the flow is laminar or it is in turbulent regime. And there is another parameter which is not mentioned here, which is basically the fluidity. So fluidity also determines that the flowability of the melt, and also its capability to fill a complex contoured engineering component cavity, I mean the die, which is also related to both the things, like it is also related to the temperature and the solid content if we are talking about a semi solid state filling, and also the melt viscosity. So, if viscosity increases, so that basically forces, if viscosity is higher, then fluidity goes down. So, in cases where that that each, but there should be a trade off, like in cases where higher viscosity and because of its because of this, slightly lesser fluidity is on demand, is the cases with the non-ferrous metals like light metals like aluminum and magnesium, where significantly higher melt velocity and lesser viscosity can cause several defects, include starting from gas absorption to dross and several others. So, that's why there must be a trade off between viscosity and fluidity. However, there are instances when even if the fluidity can also be increased and viscosity can be decreased, because by by applying the shear force to the flowing melt. Even in case the melt is having at least maybe 30 to 35% solid, even in that case its viscosity can be brought down significantly by taking the advantage of shear thinning nature of the semi solid slurry, the solidifying slurry. So, that we will discuss in detail in subsequent slides in this class. So, that can also be achievable, and because of this shear thinning property, it is possible to fill the complex contoured engineering component cavity even in with using the semi solid melt. We will come to that. Okay. Like we have discussed about the viscosity, which is a quantitative measure of the fluid's resistance to motion, the flow. So, viscosity is of two types. So, number one is dynamic viscosity, so which is generally expressed by mu or eta. So, that is nothing but the shear stress divided by the shear strain rate. So, it is basically the expression which is also shown with different notation over here. And then when we are talking about kinematic viscosity, so kinematic viscosity is nothing but when we divide the dynamic viscosity with the density of the fluid, we basically get the kinematic viscosity, which is expressed as nu over here. So, viscosity is measured using a rheometer. So, there are several different kinds of rheometers or viscometers available, which can be utilized for this purpose. We will come to that. We will discuss about the different rheometer available in practice. So, the mechanism, basic mechanism is shown over here. So, you can see this is basically a velocity distribution of a typical flow, which is shown over here. So, you can see that the fluid immediately analogous to that. So, viscosity velocity increases as it is moving further from the wall. So, this is the attribute that this is because in case of infinitely thin fluid layers. So, we will come to that. So, before so to understand the die filling well, we need to understand the viscosity models. That is because that is intrinsic, which because it is the thing which is determining the flow characteristics of the solidifying liquid melt or superheated liquid melt. So, so there are different viscosity models, like in case of Newtonian model. Newtonian models assume constant viscosity regardless of shear rate, which works for many simple fluids, like for example, water is considered as a Newtonian fluid. And then non-Newtonian model, the change in viscosity accounts for the varying shear rate. Many molten metals exhibit non-Newtonian properties. Okay. So, non-Newtonian, again that can be classified with several different variants, we will discuss subsequently, and many non-Newtonian properties include power law, cross viscosity model, Bingham model, etc., which are so all non-Newtonian fluids are discussed over here, shown in this table. So, in Newtonian viscosity is constant. In Bingham plastic, shear stress is equal to shear stress at 0 shear plus viscosity into shear strain rate. So, requires yield stress, that is the yield stress value fits many slurries, and then there is power law model. Power law is equal to eta, the viscosity, dynamic viscosity, which can also be expressed as mu, like I have used in the previous slide, is equal to k gamma dot to the power n, defines the shear thinning behavior. Then Arrhenius model, viscosity is equal to A into e to the power b by t. So, it depends on temperature, and so Arrhenius model speaks of dependence of viscosity of the fluid on temperature. Like if you are applying it to solidifying liquid melt, then it establishes a relationship between the temperature or solid fraction of the slurry with its viscosity, whereas power law establishes a relationship with the shear rate the solidifying melt or the superheated melt is undergoing it establishes the relation between shear rate to the viscosity. And then in case of cross model, it captures the non-Newtonian effects which is expressed over here. So, so again, which is a function of shear rate alone. So, our objective is in our in solidification, because in case of die filling, the melt which is filling the component cavity. So, it is not only subjected to the shear strain shear rate, but also it is basically continuously losing its superheat, and it is going below. If we are talking about a alloy, then it is continuously going below the liquidus temperature, at least in certain locations, at least in certain locations of the flow front. So, that means the moment it is going below the liquidus temperature, that means the solid starts to form. Like for example, if you talk about a very simple alloy and we talk about a Lenz diagram, and then if it is for a particular alloy, if you say this is the liquidus temperature of the alloy, this is the solidus temperature of the alloy. So, the moment at some locations the melt drops, the temperature drops below solidus temperature, that means the solid formation starts within the melt, and to account for that, so that means you have to have the viscosity as a function of both shear rate as well as temperature, or which is also a function of solid content. So, so either of the, so the viscosity model which is going to be implemented to investigate the die filling, they should be the viscosity model should be sensitive to both shear rate as well as temperature or solid fraction, to give a clearer picture about the filling capability and the viscous evolution of the melt when it is flowing within the mold cavity. Otherwise, it will not give the clearer picture. So, that we will see how in the subsequent slides in the class. So, we will discuss about how we can develop such models which are sensitive to the viscosity temperature or solid fraction as well as shear rate simultaneously, and that can lead to the much improved predictions. This is temperature, this is concentration. So, the turbulence, now next thing is the turbulence models, because often like in case of high pressure die casting, if we take the example, often we see that a turbulent flow of melt within the die cavity that happens. So, that is why it is very important to study the die filling capability of the melt. So, for that turbulence model understanding is also very important. So, turbulence effect can lead to air entrapment, and that is what I have discussed also. So, because of that air entrapment, it can cause microporosity formation, and it can also cause dimensional, it can facilitate losing dimensional stability of the developed part if it is subjected to subsequent heat treatment. So, it is a challenging thing that we experience in case of die casting, and that air entrapment can be reduced by effective die design, at least in case of, like for example, in case of light metals like aluminum or magnesium, we can basically try to adopt the principles of non-pressurized gating system, and then if in that case even we can achieve relatively lesser turbulence even in case of high pressure die casting or even in case of gravity based die casting processes. And so, if we talk about turbulence model, there are two major turbulence model that we are generally being used. for simulating the turbulent flow and more specifically turbulent melt flow. So number one is LES model. So large eddy simulation, LES models larger turbulent structures while modeling smaller scales. It is more computationally intensive but offers greater accuracy, making it useful for complex flows and detailed studies. And another variant of turbulence model is RANS, is the most used turbulence model that averages the effects of turbulence on the flow. So it simplifies the calculations using time averaged equations mostly used in case of dye filling analysis. So so going ahead, so we are basically discussing the derivation of continuity equation, which can, if there is a mass exchange involved, we can also term it as conservation of mass, and when there is no mass exchange involved, then it reduces to the continuity equation. So for example, if I bring your concentration to this fluid element in space, so you can see the flux entering through the x axis. So it is basically, so this is the x, and here so this direction, this is the y, and this is the z axis over here, and this is how the fluid element is positioned. So here assume we are focused to a point in at the middle of this fluid element. So then the flux entering within the this control volume, we can add. So this distance from the center, so the total distance along one side is delta x, along the y axis it is delta y, along the z axis it is delta z, and this because this point is located in the middle. So from any of the faces, the distance is half of the total distance between the consecutive x or y faces. So from this point along the x, the distance is delta x by 2, which can be termed as like this, delta x by 2, and then along the y z axis it can be termed as delta z by 2, and along the y axis it can be termed as delta y by 2. Okay. So so we have the distances. So then we can basically so here the fluid which is leaving the control volume. So we are considered its contribution as negative, and then the fluid when the entering side of the within the control volume, we consider its contribution as additive, and then we are focused about the net generation or the storage of the fluid within the control volume. So then we need to deduct from this value which is leaving basically from the east face of the control volume, and say this is the west face of the control volume. So then rho u, so this term comes here, rho u minus del rho u del x 2 into del y del z minus in case of x direction minus rho u plus, so this term goes here, plus del x rho u del x by 2 del y del z plus again for the y which is leaving, that means which is leaving from this direction. So rho v minus this term comes here minus del y rho v del y by 2 del x del z minus so del rho v plus del y rho v del y by 2 del x del z. Similarly, it is treated for the z direction, and we already know the rate of increase of mass in the fluid domain can be expressed as del t del rho del x del y del z, which becomes equal to del rho del t delta x delta y delta z. So then we can basically equate this with the net generation that we have calculated over here. So let us see how we proceed. So because you can see over here that so all those terms because there is a minus sign involved, this term gets cancelled out, this term get cancelled out, this term also get cancelled out. So then, and because there is a half involved, so basically what we are getting over here, we are basically getting as so here we are getting as del x rho u delta x delta y delta z, and so and then minus del y rho v delta x delta y delta z del z, and then minus del z rho w del x del y del z. So if you take del x del y del z as common, so then we basically get and so if I take minus del x, del y, del z as common, so we can achieve that del x rho u plus del y rho v plus del z rho w. Okay. This is what we are getting. So, we are equating with this we are equating basically the del rho del t delta x delta y del z. So, then if we just strike it off and then take this into this side. So, then we are basically getting del rho del t plus this is grad rho u is equal to 0. So, this is what the expression we are writing in the next. So, this is del rho del t plus grad rho u is equal to 0. So, this is basically, so in case of incompressible fluid and also in case of steady incompressible fluid. So, if this term get cancelled out, it becomes 0, and then because density is compact constant. So, it reduces to del grad u is equal to 0. So, then that is what is written over here. So, this is in the vector rotation, and in the when we drop the vector rotation, and then we can write it as divergence u is equal to 0, which is nothing but del u del x plus del v del y plus del w del z is equal to 0 in the longhand notation. So, this is what the continuity equation is. So, this is of very much importance in case of dye filling analysis when we are talking about in flow of incompressible fluid, and when density is not changing with space and time, and because we are also talking about steady and incompressible fluid. So, that time this continuity equation comes into play. However, when there is a solidification is involved, that means the mass transfer is happening. So, then we have to use the conservation of mass in that case. We will come to that. We will also discuss about the corresponding case studies. So, now we will talk about the entrained air defect that we generally encompass in case of die casting, like we have discussed during the casting section as well. So, here in this case air bubble gets entrapped in the casting due to the turbulence and other phenomena. So, the entrained air is modeled through following the appropriate equation, and the entrained air should have passage to exit the cavity through either the riser or vents, otherwise it can accumulate and create porosity, while solidification of the component and continuous monitoring of die design and pouring techniques can help mitigate this issue. So, this is a case that is the entrained air defect. This can be largely eliminated by appropriate design of the die and the gating arrangements, so that we provide appropriate escape route to the that air which is getting entrapped within the liquid melt. So, sometimes it becomes very difficult to avoid the entrapment of liquid the air pockets, like there as I told you that there are sources within the mold cavity itself, because of the in case of sand molding it is the binder ingredients. In case of permanent mold also there are some, like we are adding the we are creating the coating which is giving it the smooth surface finish, and also facilitates non-sticky behavior of the solidifying melt with the die wall. Even these are the source of some gas evolution because of some amount of burning or sublimation evaporation. So, that gas so sometimes it becomes difficult, even if we create the if perform the casting in vacuum environment, then it becomes too costly. Even if we do it in inert environment, still there are some chances instances of some amount of gas absorption within the melt. So, we have to do appropriate degassing, that is a technique which is by the melt processing, and moreover we also need to provide the appropriate escape avenue for the air which is trapped within the the bubbles which are trapped within the liquid melt. So, here this is a mechanism which is shown of the removal of the bubbles from the liquid melt which are travelling towards the towards the free surface of the melt in the riser, and then they are escaping because of the buoyancy force. And also there can be some air vents that need to be provided within the within the metallic mold, so that that these bubbles, these airs which is trapped within the liquid melt can get an escape route. So this is how we can I mean circumvent to this issue. And then there is free surface defect. So free surface defect is another major problem that we experience in case of die casting, and that again that can be largely minimized or decreased when we do appropriate die filling study. So the free surface defects occur when the molten metal surface is exposed to air during casting, leading to oxidation or the entrapment of air, gases or other impurities. And free surface defects can significantly affect the mechanical properties of a cast part, such as reducing its fatigue strength, tensile strength and overall durability due to the formation of discontinuities or inclusions. And then they are estimated by casting analysis software using volume of fluid model, where it track the interface between molten metal and air, predicting the shape and movement of the free surface during the casting process. So here these are certain examples of the free surface defect that can be originated, and that originates within the solidifying cast part, which can be significantly altered or decreased by reducing the exposure to the air to the molten metal surface, and thereby we can decrease these chances of free surface defect formation in the solidified part. So again that can be decreased, if not completely removed, then it can be brought down to its minimum possible level by appropriate design of the dies and the gating geometry. So then we are moving into the porosity. So porosity, as we told, as I discussed several times before. So these are small voids or pores that form within the casting during solidification. So these voids are caused by trapped gases, shrinkage or inadequate feeding of liquid melt into the mold. And so reducing porosity involves controlling gas content in molten metal. So that can be done by degassing or by imparting inert atmosphere. Optimizing mold design for better feeding, using risers to compensate for shrinkage, that is for that is to deal with the shrinkage porosity, and and also the better feeding, that is riser design again to compensate for the shrinkage porosity, and gas content which is the and then again the controlling the viscosity and the melt flow velocity within the mold cavity. It can be useful to control the microporosity, that is the gas porosity, which is responsible primarily for microporosity, that can be controlled in that way. So all the different kind of defects that generally generates in case of the cast part, including which is largely concerned with the porosity, can be alleviated or significantly brought down by effective design of the die cavity. So porosity can reduce the mechanical properties of casting significantly. It also significantly decreases the density of the cast part, and thereby because of this porosity present, it can serve the it can also cause significant, the cast part can behave as a brittle manner, even otherwise if it is a ductile material, but even if the casting process and the design of the dies are faulty and that causes porosity formation within the cast part, then it can show catastrophic failure also. And also along with tensile strength and hardness, ductility, it also poses significant reduction to the fatigue resistance and causes general structure weakness. So so these are the difficulties that we generally deal in case of porosity. So apart from these structural attributes, it can also cause significant downgrading of the electrical and thermal properties as well, because of the improper connection between the conducting particles. So that is also happens due to the presence of porosity. So it is very important to study porosity and also trying to find a way to nullify the presence of porosity within the cast part. So so first of all, porosity, apart from shrinkage porosity, the major problem in case of porosity that comes with the microporosity, that sometimes becomes even challenging even after improper design of the gating system and riser design, because I mean this generally happens due to the flow attributes and the gas absorption attributes of the liquid melt within the mold cavity. So it is microporosity is generally caused by the gas bubbles which are in terms of microns and usually get entrapped between the grains. So here you can see in this microstructure, so the intergranular spacings, I mean the last solidifying regions, that means the eutectic regions, within that eutectic regions you can see the origination of microporosity. So you can see, it is interesting to note that their location at the grain boundary triple point. So I mean this is the so region where otherwise the solute also gets concentrated, and this is also the region where the porosity gets concentrated. So I mean low temperature casting can help in lesser microporosity and reduce turbulence. So that is also why we are advocating the case of low superheat casting. So LSC, that is also being developed within the scope of our research group. I mean the students and the audience is welcome to look at our papers in that direction. And then the Niyama criterion is commonly used to estimate microporosity formation. So it combines the cooling rate and the thermal gradient during solidification, which can be expressed as capital N, which is equal to G by root over R, where G is basically the thermal gradient during solidification, typically measured in degree centigrade per mm, and where R is the cooling rate, typically measured in terms of degree centigrade per second, and N is the Niyama value, so indicating susceptibility to microporosity formation. So this is how we can estimate the Niyama criterion. I mean this also we discussed earlier. So so we will further discuss about the porosity modeling. And so like I discussed in the previous slide, like you can see about these locations. So these are the interdendritic locations where basically these porosities gets trapped. These bubbles gets trapped, and they later on while solidification of the part evolves as microporosity. So so these bubbles also, their shape is totally dependent on the evolution of the microstructure. So their shape, their radius of curvature changes as the secondary dendrite arms. So here these are basically the primary dendrite arm, and that means the trunks of this tree. So these are primary dendrite arm, and these are basically the secondary dendrite arm. So they are so these porosities are basically getting localized in the vicinity or in between the secondary dendrite arms. Okay. So then you can see that there is a significant impact of the PDAS, that means the primary dendrite arm spacing. This spacing between the central line of both the primary dendrites is expressed as PDAS, and then the spacing between two neighboring secondary dendrite arms, which is generally expressed as SDAS, secondary dendrite arm spacing. So they have a bigger role in the evolution of the shape and size of these micropores over time in the course of solidification of the liquid melt. So we will discuss in detail about the porosity formation, mathematical description of porosity formation model in the next class. So we are stopping here today. For the interest of time, we are stopping here, and we will continue with this in the next class. Thank you.